Hello students, welcome back to this new session on mathematics. Here I have come up with new topic of Laplace transform. That is, in this topic we'll be learning to take the Laplace transform of unit step function, okay? Or it is also called Heaviside function. I have written here as you can see it in your screen. Now here first we have to understand what is unit step function or Heaviside function. So definition is as written on your screen. Just see, the unit step function, it is denoted by u of t minus a, or it can also be written as h of t minus a. H stands for Heaviside, u stands for unit step, okay? Now it is denoted like this, and it is defined to be u of t minus a is equal to, it will be 0 when t is less than or equal to a, and it will be 1 when t is greater than a. That is, if I just show it graphically, it will be something like this. Suppose this denotes your t, and this y-axis you can take as u of t minus a, Heaviside function. Suppose this is origin for you, and here he says what a is any positive constant we are saying. So let us consider this is a positive axis for us. So let us let be standing here, okay? So up till here it will be 0 only, okay? For equal to a is also it is 0. Just as it crosses that a point 0.00000 somewhere 1, there it will turn to be 1. So we cannot exactly show it. So if this is suppose 0 comma 1 over here, it will take the value 1. So this is the graphical representation of unit step function, okay? So as you just cross that a, you will get that unit step function value to be 1. Otherwise before that it will be 0. Okay, this is the definition of unit step function, okay? Now we will learn how to take the Laplace transform of this, and what is the Laplace transform of that unit step function, and where we are exactly using this, okay? So let us work for that. Now let us understand how to take the Laplace transform of unit step function, okay? The Laplace transform of unit step function is denoted as usual as L of u of t minus a. Now you know the basic definition of the Laplace transform and also the definition of u of t minus a. First let us write that the basic definition of the unit step function. You know it is 0 when t is less than or equal to a, and it is 1 when t is greater than a. Just write it in one side, okay? And basic definition of Laplace transform you already know. So I'll just use it and let us solve that. So integration from 0 to infinity, as per the basic definition of Laplace transform, it is defined to be integration from 0 to infinity e to the power minus st into f of t. In place of f of t you have got u of t minus a dt. Is it not? Now this is equal to, now I have to split this integral because u of t minus a has been defined in two ways. For t going from 0 to a, from 0 to a it is 0 only. I had shown it in the figure also. It is 0 only. And for t greater than a to infinity is, it is taking the value 1. So integration from 0 to a, let us split it like this. E to the power minus st, its value is 0 here, dt, plus under integral sign from a to infinity, e to the power minus st, the value for u of t minus a is 1 in that part, dt. Now this is already 0, means what? The integral value will also be 0. So you'll be only left with one term, that is integration from a to infinity e to the power minus st dt. Into 1 it is dt only, right? So now let us integrate this. It is e to the power minus st divided by minus s. Integration of e to the power minus st is what? E to the power minus st divided by minus s with limits from a to infinity. If you put a as t as infinity, t is varying from a to infinity. When you put t as infinity, e to the power minus infinity will be 0. The upper limit is 0, minus 0, minus the lower limit. When you put t as a, it will be e to the power minus sa divided by minus s. Okay, so minus of minus plus e to the power minus sa divided by s. So this is the Laplace transform of the unit step function or Heaviside function. Laplace transform of unit step function is e to the power minus sa divided by s. Okay, now we will learn the property of Laplace transform. Okay, just see this. So here you will study one important property, mark it as important. So if L of f of t, suppose you are having one function f of t and its Laplace transform, you all know it to be f bar of s as it is written here, okay? Then the Laplace transform, that is L of f of t minus a into u of t minus a, that is the product of these two functions and both in the same type, that is u of t minus a you are writing the same way you should write f of t minus a. It should not be f of t, it should be f of t minus a only. Okay, if it is so, if you want to take the Laplace transform of this kind of product, it will be always equal to e to power minus as into f bar of s. This f bar of s is the Laplace transform of f of t and e to power minus as should be accompanied with that. Okay, this is one of the important properties and using these we will be solving numerous problems, so pay attention all of you. So let us solve this, let us prove this. So the Laplace transform as per the definition, f of t minus a into u of t minus a, by the basic definition let us simplify it. Integration from 0 to infinity e to power minus st. In place of this you have f of t minus a into u of t minus a dt. Okay, but we know what is this unit step function. It is actually 0 when t is less than or equal to a and it is 1 when t is greater than a. You know this very well. So according to this, again I will, because I don't know anything about f of t. F of t is any general f of any function whose f bar of s, whose Laplace transform is known to us. It is f bar of s for us. Okay. So how it will be behaving in t minus a and all, that we don't know. But we know its Laplace transform. Keep it aside. But according to this u of t minus a, let us split this integral. Okay. However, this is in product form. When u is 0, definitely this integral will also be 0. Okay, so no matter what is f of t there, integration 0 to infinity e to power, okay, let us, we have to split here, 1 minute, it is not infinity here, integration 0 to a e to power minus st, f of t minus a as it is, but this u of t minus a in this interval is 0 dt, plus under integral sign from a to infinity e to power minus st, f of t minus a into u of t minus a is 1 into dt. Won't you get something like this? Okay. Now already this is 0 because 0 into this f of t minus a into e to power minus st, again 0, 0. Definite integral of 0 is again 0. That all those things you all know very well. So directly we will take integration a to infinity e to power minus st f of t minus a dt. Now this is not a simple term. It is u of f of t minus a here. So I will change the variable here. I'll take let t minus a to be equal to some another variable, say v. So that when t is equal to a, v will be what? 0 or no? Right? Similarly, when t is equal to infinity, when you put t as infinity, infinity minus a, infinity is already, you don't know v, so definitely v also be infinity, and differentiate this, dt will be equal to dv. Let us substitute all that in this given integral. So you have this to be equal to integration from when t is a, v is 0, so 0, when t is infinity, v is also infinity, 0 to infinity, e to power minus s as it is, you are substituting t minus a as v, so what should be t from there? V plus a, yes or no? So v plus a we have to write into f of v, because t minus a you are writing v, and dt as dv, like this. Okay, now this is equal to integration from 0 to infinity, let us multiply and split the terms, e to power minus sv into e to power minus sa, is it not? Into f of v dv. Now this term, is it containing some v or something? Because we are doing the integration with respect to v, dv we are writing, look at that. Okay, means what? Any term which is independent of v can be taken out because it will be constant for it. So this will be equal to what? E to power minus as, integration from 0 to infinity, e to power minus sv, f of v dv. Is it not? Now what is this? Is it not f bar of s? Only in place of t you have got v. Is it not? So it is what? E to power minus as into f bar of s. This completes your solution for this property, and by using this we'll be working with numerous problems. Continue in my next session. Thank you.